Okay, well, thank you all for coming. So I'll talk about regret learning and bounded rational inductive agency, which are kind of two notions of inductive rationality that apply to a kind of very similar, basically the same kind of framework for decision making. So here's kind of the plan for what I'm going to talk about. So I'm first going to describe this problem setting, which is basically just a multi-armed bandit problem. So there's also like adversarial, though yeah, we can discuss whether that's a great term for it. And in these problems, I'm kind of specifically interested in issues of kind of bounded rationality, then these kind of paradoxes that arise if you allow for the environment to refer to the agent and then the agent having to reason about that, like Newcomb-like problems, and kind of whether counterfactuals are well defined or how you can use them to reason about decision making. And then I'm going to describe mainly two approaches to kind of what it means to be a rational learner in this type of setting. The one is regret learning, which is kind of a relatively well-known idea. Then depending on whether we have time, I might also talk about a kind of relatively simple idea for dealing with these based on importance-weighted estimation. And then I'm going to talk about bounded rational inductive agents, which is my own work. Okay, so let's start by discussing the problem setting. So generally, kind of we just repeat kind of at each time step, we have an agent, and the agent faces kind of a list of actions to choose from. I'll generally represent them with these boxes, usually in multi-armed bandit problems. They're called arms. But I'll represent them with boxes, and they have some, I don't know, you have some kind of description that maybe you can use to make inferences about how good the different boxes are. So in this case, the boxes have different colors, and maybe you can kind of learn what these colors tell you about the reward. And then the agent has to choose one of these boxes, and it then gets a reward for the box that it picks. And crucially, it doesn't get a reward for, like, it isn't being told the reward of any of the boxes that it doesn't pick. So you only observe the reward of the box that you do pick. And then kind of at the next time step, you again face a list of options to choose from. You have to again choose, and so on. So at any given time step, you kind of have this history of choosing different boxes and getting rewards, and from this history you have to kind of figure out what box to pick at the new time step. Yes?
Different sets of boxes at different time steps?
Yes. You could also have, I don't know, you could also have the same set at each time step, but you have kind of different, usually you have these kind of contexts, so there are these contextual multi-armed bandit problems where, I don't know, maybe you have the same set at every time step, but you have a piece of paper next to it that kind of, I don't know, says something about what's in the different boxes. But that's kind of all equivalent. Okay. So the goal is for the agent to learn to choose the best box at each time step, and for the most part, we'll imagine that the agent kind of wants to choose the myopically best box. So when it chooses a box, it just thinks about the reward that it gets right now. So if there's some kind of, you might imagine that there's some kind of hidden mechanism behind all of this, that if you choose the yellow box, then maybe at the next time step you get a lower reward. For the most part, we'll imagine that the agent doesn't care about this and kind of still wants to take the yellow box if it gives the highest immediate reward. Though, yeah, I think one can modify this to make it work without this, but it's easier to imagine it in this setting. Okay, and then the kind of meta goal is to specify what it means in this kind of setting to be a rational agent. So I guess one way of looking at this is that you look at an agent that's facing this kind of problem. You look at it from the outside. You see what they do. You see the rewards, and kind of can you say, like, is this agent behaving reasonably? Okay. So here's like a kind of very conceptually simple example of such a setting. So I'd say at each time step you just have these 10 different boxes to choose from. And at the beginning of time, oh yes?
Sorry, just when you said rational learner, is what you mean is just do I find an optimal strategy for a learner?
Repeat the question.
Okay, so the question is, when I say rational learner, do I mean find an optimal strategy? So
yeah, the optimal strategy could require more computational power than you have. Or you could be like, since you haven't specified anything about the boxes, maybe the boxes are just trying to mess with you specifically, and some, less intelligent thing that isn't correlated with you would get a good score. And so you still kind of want to say that maybe you're behaving rationally, even though you have a lot of regret relative to something simpler.
Yeah, that's basically the answer. Yeah, okay, I have to repeat it for the audience at home on TikTok. So the reason why kind of learning the optimal strategy is not
as simple as it looks.
Yeah, it's not as simple as it looks, or kind of isn't kind of the complete answer. The reason for this is that, yeah, sometimes the optimal strategy is one that is very difficult to compute, and then you still want to say, like, if the agent learns some simpler strategy that's maybe kind of relatively good for how much compute it has, you still want to say that the agent is kind of doing well, is behaving rationally, given that it has these constraints. And then the other thing is that you could have these kind of crazy environments that like they run exactly the source code of the agent, and then they kind of they put like no reward in the boxes that the agent picks. And then the agent is kind of just screwed, right? The agent can't really do anything. But you can't really fault the agent for that. You have to then still kind of make sense of the agent's behavior and kind of make it so that the agent can still behave rationally in these kinds of problems. Yep.
My question is, like, what is the definition of rationality?
Yeah, I mean, that's okay. So that's basically that's kind of the question that the theories are supposed to answer. It's like, given that these things are kind of tricky, yeah, what does it mean to be rational in some sense? Like, what are some sensible notions of rationality? Okay. Okay, but before getting to the kind of the weird problems, let's maybe look at a really simple problem. So let's say that at each time step there are just 10 boxes. And the way the reward works is as follows. So at the beginning of time, the environment generates 10 numbers, somehow at random, for example, uniformly from the unit interval. And then at each time, if you choose one of the boxes, the reward is sampled from a normal distribution whose mean is, well, the kind of corresponding number that the environment generated in the beginning. So kind of each box pays off, well, something that you don't know plus Gaussian noise. Okay. And in this case, it's kind of clear what you want a rational agent or rational learner to achieve, at least kind of in the limit. You should just learn to, or you should somehow be able to figure out after some time which box is best in terms of these means. And then always take that box, or takes that box with limit frequency 1.
Whoa. I thought you said we were in a myopic setting here.
Nice.
This doesn't sound like myopia.
Yeah. So that's oh yeah. Okay. So what John remarked is that this doesn't sound very myopic. And the reason why it doesn't sound very myopic, assuming I understand what John means, is that, well, let's say in the first, I don't know, you do this for like 100 time steps, and then you conclude that the box 10 is the best. Well, maybe you should just take box 10 now, right? Because myopically, that's just the thing that you think is best. But the thing is, if you only take box 10 at some point, then you are not going to learn if one of the other boxes is actually better. Right? So you have to do some kind of exploration, which isn't so easy to justify if you're not if you are myopic, right? Because the reason you do exploration is that kind of in the long term you want to figure out what's best. I assume, is this what you meant? Yeah. So this is an issue. I'll defer this to the discussion. I think I'll defer this to the discussion because I think it requires more to say. It'll become clear how the rationality criteria kind of enforce this, but it is still it is definitely an issue. Okay, so I guess I already said this to some extent. If you do want to kind of learn to choose the best arm with like almost all of the time, you need to pull each of the arms infinitely often, because if you choose the box number 1 only 1,000 times, there's some positive probability that you kind of just got unlucky and got very low, like unusually low values for box 1, and like kind of actually box 1 is the best one, but you just can't tell based on the data you've seen. And if after these 1,000 steps you kind of stop taking box 1, you never learn that it is actually best. So if you want to kind of guarantee optimality in the limit, you do have to take each box infinitely often. Okay, and then there's the question of kind of like how quickly can you learn to choose the optimal arm and stuff like that. And for this will not matter for the purpose of this talk, but there's lots of literature on this. Okay, now there are more kind of conceptually interesting cases of environments. So here's kind of a typical bounded rationality example, which maybe you've seen. So let's say that the boxes have descriptions on them that specify in some language like in some kind of mathematical language what reward is in those boxes. And so the left box says 0.4, and it just always has a reward of 0.4. And the right box gives like some digit of pi, and says like the reward is that digit of pi, and it's a binary digit of pi, so it's either 0 or 1. And kind of, in some sense, what you want to do, right, is you want to take this box if that binary digit of pi is 1, and you want to pick that box if it's 0. But maybe you can't do that because probably it's hard to compute the 2 to the 100th binary digit of pi.
You have digit extractors for that, actually.
Not 2 to the 100.
They're log speed. You don't have to.
Are they logs?
Yeah.
Go on.
So if you had 2 to the 100th, then this would be a better game.
Are you sure that's the log speed thing is right?
Sure, yeah.
Okay. I thought it was like linear in the, but okay.
If it was linear, then there wouldn't be any point in having a digit extractor in the first place.
I think you should go on.
Okay. So let's assume, perhaps contrary to reality, that this is kind of very difficult to compute. Then, yeah, usually you won't be able to follow this policy, and like the policy of choosing this one if that digit is 1. But kind of intuitively, it seems that, maybe you think that digits of pi are uniformly distributed, which I think they aren't known to be, except empirically. Like empirically they are, but I think there's no proof that the digits of pi are uniformly distributed. But if you think they're kind of uniformly distributed in some sense, then it seems kind of reasonable to pick the right box, right? Because in some sense its expected value is 0.5. Okay, and then you can have these kind of funny problems of the environment kind of referring to the agent. So here, the left box always pays 1/2, and the right box, well, it's 1 if the output of this specific program run with this problem as input is the left box, and it's 0 otherwise, and this program happens to be exactly what the agent is doing. Then, yeah, it's kind of tricky, right? If you're this agent, you're following this computer program C, what should you do? Well, it seems kind of clear that you shouldn't take the right box, because then you just get a reward of 0. So it seems you should take the left box, but then that's also kind of weird, because if you know that you choose the left box, which kind of in some sense you should know, right? Then you kind of also know that in some sense you could choose the right box, and that would give you some kind of counterfactual reward of 1. Okay. Okay, so that was all on the problem settings part. Any questions at this point? Okay. Okay, so now we're going to get to the ways of defining notions of rationality for these problems. And I'll first kind of briefly describe a kind of high-level idea that a lot of these different approaches have in common, which is that they define rationality relative to some hypothesis class. So you have you consider some set of hypotheses, and these hypotheses are some kind of objects that somehow can tell you what to do. Maybe they can tell you other things as well. So some examples, you could have something like all polynomial time computable hypotheses, or like, I don't know, all polynomial time algorithms or something like that, or all algorithms that take only 10 seconds to run on your laptop or something like that. And so that's kind of how these approaches allow for kind of bounded rationality. You can just restrict your hypothesis class to relatively simple or computationally simple algorithms. But you can imagine lots of other things. So for example, you could just have it that you're making some decisions and you have 3 friends, and these 3 friends, they give you advice on what you should do, and you just want to kind of learn to be kind of rational relative to these, which kind of just means like, I don't know, in some sense you want to figure out who of them is kind of most right, like most correct about what you should do, and you should follow their advice, or maybe you should aggregate their advice somehow. Okay, and generally this hypothesis set is imagined to contain some hypotheses that are false. So yeah, there's some, like for example in the friend's case, maybe you have one friend who actually, I don't know, you get advice on like what job you should take, and you have one friend who has just no idea what they're talking about, but they still just tell you stuff. And like part of the, like you have to figure out that they don't know what they're talking about, and you have to learn to stop listening to them. Okay, and then the idea is that you have some rationality requirement that defines rationality kind of relative to this class, and usually it's kind of very roughly of this form that, again, in some sense you're not you shouldn't be outperformed by anything in this hypothesis class, where the kind of the part that is left open is kind of like, what does it mean to be kind of outperformed by something in this class? And that's kind of what the approaches that I'll describe specify.
So what did the hypothesis describe? Did it describe what the distribution of the boxes or?
So that also varies a bit between the different approaches. I think that like the minimum thing is that they.
Repeat the question.
Oh yeah, the question is what exactly do the hypothesis describe? Yeah, I guess this varies between different approaches. I guess the minimum thing is that they. I mean, even that's not clear, but like one minimal thing that you can think about is that they just tell you what to do. So they just output at each of these, like you face 5 boxes and each of the hypotheses just tells you like you should choose the leftmost box. But you can imagine other kinds of hypotheses that also make predictions about the reward that you're going to get or something like that. Okay. And so the way that you get these, like the way that you're able to deal with bounded rationality, for example, is that if you only have kind of relatively simple hypotheses, then you might be able to kind of not be outperformed by any of the hypotheses without having to do anything super complicated yourself. What's the?
Oh. Keep going.
Okay. Okay, and yeah. Probably the example of this that most people know best is Scott's logic induction framework, where this outperformance criterion is it's called exploitability, right? No?
Yeah.
Yeah.
I don't know.
Okay. Okay, and then in this talk there'll be regret learning and bounded rational inductive agents. Okay, and for the purpose of this talk, I'll assume that the set of these hypotheses is actually finite, which seems a bit odd, but for the kind of approaches in this talk, it just doesn't make it much more complicated to consider the infinite case. It's just kind of a counting burden that isn't very interesting to discuss. Okay, and then people have different names for these hypotheses. So for example, in the logic induction framework, these would be traders. In the regret learning case, they were experts. In the rational inductive agents case, they're called hypotheses in the paper, but we also sometimes call them bidders.
So negative example, you also said?
Oh yeah. So an example of an approach that kind of doesn't work, like that isn't like this. This is like not supposed to be a theory of rationality, but if you just train a neural net, you train a single neural net to make predictions, or you train it with some Q-learning thing or whatever, then like there's no hypothesis class or anything like that. You just have this one object that you're kind of incrementally improving.
I think the right way to say would be we don't know what's the hypothesis class, and there is no hypothesis class.
Maybe, yeah.
Could probably come up with one. Could come up with a hypothesis class where all the hypotheses are just really bad.
Right, yeah. Okay, that's true, yeah.
What I meant is that there's probably some natural space of hypothesis which neural networks have learning guarantees with respect to. We just don't really understand what this space looks like very well. But yeah.
Okay. So should I do the break now, or what's the?
Yeah. Yes.
Okay.
Break. So yeah, we'll do a 5-minute break. Everybody has to leave the room and then come back. I'm going to bang the gong in 4 minutes. Go for it.
Okay. So I'm going to start by talking about regret learning, which is one of the approaches to kind of saying what is rational to do in this type of problem. Okay. So. Yeah, maybe I'll go a bit over what exactly the definition is. So So a bandit problem kind of specifies at each time what the boxes are, like including kind of like what description each box has, or like what color or whatever. And it also specifies a function that maps the boxes onto rewards. And this is allowed to depend on what the agent did in the previous steps. It's called a reactive bandit. Okay, and then an expert is something that specifies at each time, like it just tells you one of the boxes and kind of, it's like in some sense, or like hypothesis, at some level it just kind of tells you at each time what they think you should do. Okay, then I'm not going to use this because it's ugly. So,
What's the difference between a reactive bandit and a Markov decision process?
I guess the reactive bandit doesn't have to be Markovian. Oh, the question was, what is the difference between a reactive bandit and a Markov decision process? And the difference is that it doesn't have to be Markovian, though, I mean, to some extent,
what happens at state n+1, what happens at time n+1 can depend on all the previous stuff instead of just what happened on turn n?
Yeah.
Okay.
Though, yeah, I mean, to some extent, this Markov condition is to some extent vacuous, right? Because there can be this hidden state that just keeps track of the history. So, yeah, I think you can think of it that way, yeah.
Is it that we're also allowing like funny business where the way the boxes work can depend on things like the agent's algorithm that you mentioned?
Yeah, so I mean, you can have this in Markov decision problems as well, right? You can have a Markov decision process where the transition, okay, you need a partially observable Markov decision process, I suppose, to do the kind of hidden state stuff. But you can have a partially observable Markov decision process or something like that where the transition probabilities happen to be computed by some algorithm that is exactly the algorithm that the agent uses. So
we could talk about that if we wanted.
Yeah. Okay, so now I'm going to say what this regret learning idea is, and it's very simple. So let's say that there are these boxes, and let's say that the agent at each time step takes box T. And let's say that we have an expert who recommends the boxes BT prime, so it's some different box, or potentially sometimes the same box. And now the environment specifies reward functions. So this reward is the reward that we actually get. And then this reward is kind of the reward that we would have gotten had we followed the expert at that time step. And now, if I had been clever, I would have written it the other way around, and then I could just put a minus sign between them. But let's rewrite it. So the regret is the difference between what I could have gotten by following the expert's advice and what I actually got. And so this is the regret at time step t to this particular expert. And then we can also define the cumulative regret, which just is, the sum over time steps of the individual round regrets to this particular expert. So this is called the regret at time t, and it's to a particular expert. Is that intuitive? Mm-hmm. Okay. more to say. Okay, yeah. And now I can also have the slide. I want to do it at the board because the slides are in Google Slides. I don't have equations. I don't have proper equations. Okay, so now the notion of rationality is just that we should have sublinear regret to each of the experts to each of the experts that we're considering. So I don't know, we have like 10 experts, and we want to make sure that we have sublinear regret to each of them. And sublinear regret, like for some reason they always talk about sublinear regret. I think this is
the
thing.
reason you talk about sublinear regret is because, like, the maximal, like if we just divided the regret by T capital, so we just took like the average rewards instead of the cumulative, sublinear means that it goes to 0, which is just like,
Yeah, basically,
like a natural condition.
you're tying over how often you have serious regret thins out to 0, and your regret on a typical round also goes to 0.
I mean, another way to say this is that any algorithm has linear regret. Like, anything you do would have linear regret. This is like the worst thing you could have. So sublinear just...
Yeah, so I understand. I think, maybe I can finish first. So the reason why I find it interesting, odd, is that one can't just say the average per round regret shouldn't be positive in the limit, right? Which I guess what you're saying is that that's basically what sublinear regret means, which I find somehow more intuitive than saying sublinear regret. But it's basically the same. It is, like, one thing is that the regret can, of course, be negative in the limit, right? If you have like a dumb expert, you'll have negative regret to the expert. So actually, this is wrong. The average per round regret shouldn't go to 0. It should just kind of be
asymptotically be 0 or less.
Yeah. Yeah. Okay.
I mean, it usually goes to 0 in the worst case, right? Like if you can choose any experts, and so usually in those theorems, like it goes something which is in the worst case.
Yeah.
For some experts, like
Yeah. Yeah. I mean, you can't. Yeah. If you just have the optimal expert in your set that just tells you what the optimal thing is, then yeah, the regret is always non-negative to this expert. Yeah.
Can you define regret with respect to a class of experts?
Like an infinite set of experts?
Like maybe some expert parameterized by, like all polynomial time algorithms.
Yeah. Okay, so I mean, all polynomial time algorithms is a kind of countable set of experts, and that you can do, yeah, and you can still achieve sublinear regret in general. You can also, you can also have some, you can have some more complicated parameterized class where like there's some real number as a parameter, and then it, like, in general becomes tricky, but yeah, they're like, linear bandits. You can Google linear bandits if you're interested in this. Okay, so some illustrations. So let's take this. Let's take this example again, where you kind of have to learn which box has the highest mean. Then and assume that you at least have the set of constant experts. So you have the expert that always recommends box 1, you have the expert that always recommends box 2, and so on. And maybe you have other experts as well that for some reason switch around, but you have at least these. Then to achieve sublinear regret, you have to kind of in the limit take the take the best box with limit frequency 1. Because if you don't do this, you'll have linear regret to the expert who happens to propose taking the correct box. Okay, now the bounded rationality example. So let's say we have to choose between some number between 0 and 1 and the 2 to the teeth binary digit of pi, which actually maybe one can compute efficiently, so maybe you have to think of this as being something else. And you have a bunch of experts. And in particular, imagine that you don't have the expert that is able to just compute that binary digit of pi. And let's, for simplicity, just consider these 3 specific experts. So there's one that always recommends the left box. There's one that always recommends the right box. There's one that does the kind of sensible thing of recommending the left box if the number is greater than 1/2, and the right box if it's smaller than 1/2. And then how can you achieve sublinear regret? Okay, so I guess the obvious thing is that you should kind of learn that the third expert is reasonable, right? It's more reasonable than the other ones. If you, for example, always follow the first expert or something like that, or always follow the second expert, you will typically have high, like, linear regret to the third expert, well, unless the yt's go to 0 or to 1 or something like that. But one thing that you can also do is you could just, like, in some sense, you can take the right box when that digit of pi is 1, and take the left box otherwise. If you do that, you still have low regret. So you're not restricted to the hypotheses that you're considering. You just have to outperform them in some sense. And you can even do, like, funkier things, let's say most of the time you compute the digit of pi and take the right box if it's 1 and the left box if it's 0. But sometimes you just, I don't know, just pick randomly or something like that. Then, okay, depending on the exact numbers and so on, you might still have low regret, like sublinear regret to these experts, because you're kind of, by being able to compute the digit of pi, you're kind of, you're really outperforming the experts, and so you can kind of
sacrifice some performance.
Yeah, sacrifice some performance on some problems, and you're still going to be better than the experts. Okay, now one thing that is relatively easy to see is that if we get to these kind of more conceptual cases with self-reference and so on, you can't achieve sublinear regret if you want to be a deterministic agent. So here we have the problem where the left box always pays off 1/2, and the right box pays 1 if you don't take that box, and 0 if you do take it. And if you, like, it's kind of easy to see that any deterministic algorithm here will have regret to one of the 2 kind of constant experts. So for example, if you kind of converge to always taking this box, you'll have high regret to the expert that says that you should actually take this box. And if you take this box some of the time, then, well, every time you take it, you get 0. So if you take it, let's say, 5% of the time, then on average you get 0.45 as a reward. And so then you have regret to the agent, to the expert that says that you should take the left box. Okay, and the solution that you need to address this problem is, as you might guess, to not choose deterministically, to choose randomly. And in particular, you need to choose randomly in a way that's independent of the environment, right? Like this problem, if you can randomize, but the environment can perfectly predict how, like the output of your random coins or whatever, then the randomization doesn't help you get around this. So you assume that you can randomize independently from the environment. And then experts may be stochastic. So they might randomly determine whether they recommend the left box or the right box. But they're not allowed to recommend probability distributions. Okay. So kind of here's an example. Like, imagine you're playing rock, paper, scissors against someone who can predict very well what probability distribution you're going to play. Then the optimal thing is to randomize uniformly. Okay, well, under some details that I haven't specified, but they're kind of, you can probably guess. And if you have an expert that just stochastically recommends one of the three, like chooses that uniformly at random, then that expert will always, like, well, on average, in the limit, receive a reward of 0 if you have the kind of typical payoffs for the game. So they'll win 1/3 of the time, draw 1/3 of the time, lose 1/3 of the time. And to have low regret relative to that expert, you have to also randomize uniformly. Okay, so even with this ability to independently randomize, it's not at all obvious that you can achieve sublinear regret. But it turns out that you can actually achieve this. And it's, yeah, I think the results are it's quite surprisingly strong. So you can take kind of any finite set of experts, and you can guarantee that in any environment, like so in any bandit problem, including reactive ones, you achieve sublinear regret with probability 1. Unfortunately, this is not so easy to prove, and it's also, like, the proof isn't, it kind of has some conceptual ideas, but it's, it's like relatively technical. So one kind of high-level aspect of the algorithm that you can probably guess is that in some sense, you keep track of the performance of the different experts. So you kind of remember how well you did when you took the actions recommended by each of the experts. And then you randomize over the experts in a way that gives more weight to the ones that have performed well. But like how exactly do you pick the probability distribution is like a bit more complicated. And then to prove that this works, you also need, you need to do lots of kind of term manipulations, basically. So that's why I'm not going to say how this works. Yeah?
So, I might be completely wrong here. So if I, instead of have the experts give, the experts are giving like predictions of reward, or they're giving recommendations?
Just recommendations.
Just recommendations. If the experts were giving predictions of reward, does this make things easier in some sense, or not that you know of?
So actually the kind of the optional example,
Yeah, you could have one that like empirically does really well, but predicts that it's going to perform very poorly. And
I guess for regret it doesn't matter.
Could you repeat?
What's the question again?
Maybe Caspar can repeat.
Okay, I think the question was, if you have experts who predict expected rewards instead of just making recommendations, does it become easier?
Easier in what sense?
So one thing is that I think one can more easily describe algorithms that are kind of reasonable in that case. And
I mean, I think that the relevant sense in which you can argue that it becomes easier is that if you're like doing model-based reinforcement learning is really what we should be calling this. Like if you have like actual models of what's going to happen, then you can have stronger guarantees, at least in the realizable case, and sometimes even in non-realizable case, you have stronger guarantees for what kind of convergence rates you can expect given a really big hypothesis class, right? Because, just the classical theory of adversarial bandits, you get red bounded scales with a number of arms. If there's tons of arms, then it's bad. So what you want is to exploit some structure on the space of arms. And you might still get it in adversarial bandits if you can assume that the reward somehow depends in some very regular way on the arm you choose, for example. So you can have theorems like that. But it's sort of more natural to really talk about hypotheses that predict what's going to happen. And then it's kind of more natural to assume that there's some regular shape to this hypothesis. So I think that in this sense it becomes easier.
So, I realized how my question was dumb as I was asking this. I no longer have a question. If there wants to be discussion on it, that's fine, but I realized my question was dumb.
Okay. Okay. Well, I'm now going to argue against this regret learning framework. So I think one kind of very straightforward point is that it requires two boxing in Newcomb's problem. So if you have this typical Newcomb's problem setup, well, except that now you choose between the left box and the right box rather than one box in both boxes. So you have one box, like the left box pays off 1 if omega predicts that you choose the left box and 0 otherwise. And the right box pays off the same as the left box, but plus epsilon. Then the optimal thing to do according to kind of evidential decision theory or any less wrong decision theory is to pick the
Finally, we have a good name.
is to pick the left box. Right, and I don't know if you're thinking about the optimal policy in the beginning or something like that, you want to pick the left box. But if you pick the left box, you have a regret of epsilon in every step to the expert who says that you should take the right box. And so you have to take the right box all of the time to make sure that you don't have regret.
I feel like there is something about this framing which is kind of misleading, in the sense that, if you take an actual multi-arm bandit algorithm and let it play a Newcomb's problem, it will actually converge to one boxing. Every time one boxes, it gets high rewarded. Every time it's 2 boxes, it gets low rewarded.
Oh, it's the difference between sort of receiving by fiat, basically in the setting where nature tells you, oh yeah, in this arm, if you had pulled it, you would have gotten blah, blah, blah. That record splits apart from the empirical record of what happens when you pick this arm.
Yeah, but that's like online learning, that's not bandits. Because in bandits, you don't know what you would have gotten.
Yeah, so it's actually not about,
Could you summarize it, or?
Sorry, the questions or? Okay, so the question is about, the thesis underlying the question is that if one actually applies a bandit algorithm to this, it would learn to pick the left box, because every time it picks the left box, it gets a reward of 1. And every time it takes the right box, it gets a reward of epsilon, I guess. Okay, so if you choose a deterministic bandit learning algorithm for the statistical case, like the statistical bandit case, then this actually happens. if you, the reason why it doesn't happen this way if you choose a bandit algorithm for the adversarial case is that you do this independent randomization. So like one very simple thing that you can think about.
Then it depends on the operationalization, because it depends on how Omega interacts with your randomness, right?
Yeah, it depends. Yeah, I probably should have just specified exactly what Omega does, though, well, actually it doesn't matter because the argument that I made is just like if we want to have sublinear regret, you have to converge to taking this, right? So like, and that holds kind of regardless of how Omega predicts what you do. But one thing that you can imagine is that Omega sees your probability distribution and kind of just samples from it, but independently from how you sample from it. And the thing is that then if you, for example, if you imagine that you're using a fixed policy of just doing 50-50, so like this to go like in the first 100 steps or something, you just do 50-50 to kind of see how good the different arms are, then you'll actually observe that the right box is better. Because the boxes are filled according to the same way in these 100 steps. Namely, this has 50% 1, 50% 0, and this has 50% 1 plus epsilon and 50% epsilon.
Oh, when you randomize into taking the plus epsilon box, you get a better score.
Yes.
And so you want to randomize into it more and more, and so you follow that off a cliff.
Yes. Yeah.
Yeah, so this is like a problem for adversarial bandits. It's not a problem for stochastic bandits.
Yeah. Though also, this is also not a, basically all I'm talking about is adversarial bandits. Yeah. Or like algorithms for.
Take the view that this is in some sense the problem. This is in some sense this would be the point of view that I would advocate, or part of the point of view that I would advocate.
Sorry, it's very interesting what I suggest Caspar continue.
Okay, yeah, maybe something for discussion.
Got about 8 minutes.
Okay. Okay, so here's another issue. Like in some sense, like regret learning uses this randomization in this particular way to induce these counterfactuals in some sense. And it has to use them that way, otherwise you can't achieve low regret. And because it uses the randomization for that purpose, it generally can't use it for other purposes. And so if you have a problem where, like basically, like in some sense your task is just to optimize the probability distribution over the boxes, and the reward just kind of, in some sense, depends directly on that probability distribution, regret learning is not going to care about the kind of direct impact of your probability distribution on the box you take. So for example, here we have a case where kind of you have to choose a probability of taking the left box of at most 1/2 to get a reward of 1 if you take this box. And if you take the left box with a probability of higher than 1/2, the reward kind of drops off. And so the optimal policy here is the right box space of 1/2, and the optimal policy is to take this box with probability 1/2, this box with probability 1/2.
But the problem here, you would be able to fix it if you somehow change the new space of arms, where your arms are the probability.
No, you couldn't, actually.
Are we on the table this? Sorry, we'll table this for the discussion.
Okay.
Keep going.
Yeah. Yeah, you can't fix it that way because you're still going to do the external randomization, basically. But we can discuss this.
We need to be on a trajectory to get to the end of this by the allotted time.
Yeah, I'll just finish talking about why I don't like regret learning, and then I just won't get to the bounded rational inductive agents, I suppose.
But that's cool.
Yeah, that seems fine. Okay. So regret learning doesn't allow converging to doing this with probability 1/2 and this with probability 1/2. Because if you do that, you have regret relative to always taking the left box. Okay. Okay, I'll finish with this conspiracy theory slide. So people often say, when they introduce this regret learning framework, that the whole randomization business is about exploration. So like you kind of take, you follow the experts that have performed well with high probability, and with low probability, or like with some lower probability, you take the recommendations of experts that have done worse, and you then kind of say like, well, we do this with some probability, and we do this because we need to do exploration. That's like something that people typically say, and I mean, to some extent that's true, right? If you don't take experts that have performed poorly in the past, if you take them or follow them with probability 0 and you have no mechanism of ever trying them again, okay, then you don't do enough exploration and you can't converge to optimal behavior. But the randomization in these regret learning algorithms actually also performs these other tasks, like generating these counterfactuals that kind of like without randomization you kind of like, I don't know, they're not even well defined maybe, or like you can't ever access them. But like that's also something that you need to do. And also sometimes you kind of randomize in a particular way just to make some experts worse, because that's what you need to do to achieve low regret. So for example, in this example where you have to choose a probability of at most 1/2, you have to sometimes choose that thing with probability higher than 1/2 to make the expert that recommends that thing bad. So it's not just about it's not just about exploration. The randomization is also about kind of these other things. Okay. I guess there's no time left to do any of the other stuff.
A few minutes if you want to.
Somewhere or advertise or something.
Okay. I'm just going to demonstrate this decision auction. So we have this alternative theory for how one might do this, which avoids some of these, or like treats very differently these counterfactual issues. And how much time exactly do I have left?
3 minutes.
Okay, so that's enough for a gimmick, like a cheesy demonstration. So here's roughly how this works. So imagine that you're kind of the set of experts, and now I'm facing a decision between these two boxes, so this pays off the 8th digit of pi, where it's kind of counting from like 3 being the 0th, 1 being the 1st, 4 being the 2nd. It pays off that in dollars. And the other thing pays off, 13 times 17 divided by 38, then the kind of next lower integer, and then that times 2, also in dollars. Okay, so that's the decision problem that I face. I'm very bad at calculating these kinds of things. Of course, I filled these with money last night, but I'm also very bad at remembering anything. So I don't know which of these is better. And now you're going to be my experts. And the way this works is that kind of I just, like by fiat, you all now earn, you get 20 logical dollars. It's a new currency. And now the way I'm going to decide what to do is that I'm going to run an auction. You have to submit your bid in logical dollars. The highest bidder gets to tell me what I do. I then do what they tell me I should do. Then I open that box. I see how many dollars it has in it. And then the highest bidder gets 1 logical dollar for each dollar that I get. So one way of thinking about this is that I auction off this security, which gives the owner of the security the right to tell me what I should do, and gives them 1 logical dollar for each dollar that I get. Okay, so maybe we can run this auction. I think maybe I should put on the board what the options are. So it's the 8th digit of pi, where this is the 0th, this is the 1st, this is the 2nd. And the other one is 2 times this, which I don't know whether people can see this. Okay, so do people feel like bidding? Who's anyone for one logical dollar? Okay, we have one, two. Do you want to bid something? $2, okay. Three logical dollars, okay. 1 for 3, 4, okay. 5, 6.
How many do we have each? 20.
You each have a budget of 20 logical dollars, yeah.
10.
Okay, we have 1 for 10. Anything higher? 11, okay. Anything higher than 11? Okay.
Once, twice.
And sold, okay. So you now have to pay me, and I'm the bank, right? So I'm just going to deduct 11 logical dollars. You get this security. Now with this security, you can tell me what I'm supposed to do. So which of the two should I take? The
Left.
Okay, so it's this one. So I'm going to open this one. And it contains $10. So now, second part of your security, you get, it's the wrong one. You get 1 logical dollar for each dollar I obtained. So you get 10 logical dollars. So, okay, so you now have, I guess, 9 logical dollars on your bank account and 10 logical dollars in cash. Okay, I guess those are the 3 minutes. But this is the basic mechanism for how this works.
The overbid, right?
Yes.
So I think that we should call the talk there and continue the discussion afterwards. Thank you very much.